Hello everyone, very good morning and thank you again for joining us today. And today we are very pleased to announce. Hello everyone, we have a very good morning, very special thank you again for joining us today. Side of the globe. And today we are very pleased. Jay Guo. Hello everyone. We have a very good morning. Very special guest, distinguished professor from joining us of the global today. Side of the globe, big data. And today we are very pleased. Jay Guo. Hello everyone. We have a very good morning. Very special guest, distinguished professor from joining us of the global today and big data. And we are very pleased. Jay Guo. Hello everyone. We have a very good morning. Very special guest, distinguished professor from joining us of the global today and big data. And we are very pleased. Hello everyone. We have a very good morning. And distinguished professor joining us of the global today and big data. And we are very pleased. Hello everyone. Very good morning. And distinguished professor joining us of the global today and big data. And we are very pleased. Hello everyone. Very good morning. And distinguished professor joining us of the global today and big data. And we are very pleased. Hello everyone. Very good morning. And distinguished sensing and communications to multi-beam antennas for 6G. And without further ado, please welcome Professor Jay Guo.
Thank you very much, Zach. Good morning, ladies and gentlemen. It's my great pleasure here to discuss collaborations with the renowned 6G Flagship, and thank Professor Marty for inviting me here. This morning went through a lot of projects being conducted at the 6G Flagship. I have to say I was utterly impressed, and also I feel excited that there are a lot of synergy we have between our two research organizations, two universities. So today's talk will focus primarily on two research topics. The first one is about integrated sensing and communications, ISAC. The other one is multi-beam antennas for 6G. So here's an outline of my talk. The first one is a quick introduction about my university, the University of Technology Sydney. Then I'll touch on 6G features and the demand on antenna research and antenna technologies. After that, I'll focus on a few research activities at the University of Technology Sydney, including ISAC, reconfigurable antenna and metamaterials, wideband and reconfigurable quasi-optical beamformers, last but not least, type multi-beam antenna. Then I draw some conclusions. A quick intro about UTS. So we have over 45,000 students in 2024, including 10,000 international students. We have 4,400 full-time equivalent staff as of March 2020. I think that's reasonably compatible with Oulu here. In the QS ranking top 100, we have been there for a couple of years now. We are best known in a number of areas, but for the interest of this audience, it's about telecom, AI, and environmental research. We have 150 plus undergraduate and 250 plus postgraduate courses, and other some discipline and emerging disciplines. We have over 210,000 alumni living in over 140 plus countries. So I manage the Global Big Data Technology Center, otherwise known as the GBTTC, at the University of Technology Sydney. We have three programs. The first one is mobile sensing and communications, on which we have a number of labs. The key ones include the electromagnetic informatics. This is focusing on antenna propagation, RF systems, etc. This is probably by far the largest group. We are probably one of the largest group antennas in the world. Currently, we have more than 20 postdocs. We have more than 20 PhD students, so a number of postdocs, altogether probably about 30 researchers in the field. Then we have radio sensing and pattern analysis, millimeter wave and terahertz systems, and UAV communications. One particular focus in this program right now is about ASAC, in particular network sensing for environment. The second program is big data analytics and machine learning. So we have a number of laboratories, natural language processing, multimedia and data analytics, visual and oral intelligence, digital twin. So digital twin is an emerging new technology which is being embraced by 5G and 6G, by all disciplines, including communication and RF radio researchers. The third program, 5G networks, networking and IoT. We have a number of laboratories. The major ones are 5G and IoT, network security, and software-defined networks. Professor Eric from my center has been visiting here, so he's leading this program. So at UTS, at the GBTTC, we are closely aligned with the global industry and have been actively working with industry for many, many years. I'll touch on this, in particular in the field of wireless communications. We collaborate with the Telstra, that's Australia's largest operator, and TPG Telecom, another operator. For the vendor, work with Nokia and Ericsson closely. Also, we work with other ICT companies like Intel, etc. So, being 6G flagship here, I'm sure you are all familiar with. This is my personal perspective. Why 6G? So, there are a number of necessities, or drivers you may call it, for 6G. To me, these are the main ones. The first one is that we are moving to the age of extended reality, digital twin, and metaverse. Then we will need terabits per second communications. So this is the first driver. The second driver is ubiquitous coverage. So the rise of LEO satellites and direct-to-device services by satellite, etc., make it possible now, maybe in the first time in our history, that ubiquitous coverage will be realized in 6G. As Marty mentioned earlier, this has been a dream of communication researchers since the first G, but maybe time is a time now we make this happen. So that's the second reason why we should have 6G. The third one is ubiquitous sensing for sustainability. So we are facing challenges, climate change. In order to manage climate change, we need to understand the world. We need to sense the world. But in order to fully sense the world from everywhere, we need ubiquitous sensors. But having this is not an easy task, because deploying many, many sensors, billion sensors across every corner of the world is very, very costly. In contrast, we will have a ubiquitous coverage of wireless communications. So this ubiquitous communication network can serve as a ubiquitous sensor. So in the first time in our history, we would be able to sense our whole world using wireless communication networks. So this is called ubiquitous sensing. This, to me, is one of the most exciting features of 6G. Then we have other features like low energy side link communications, meaning devices can communicate with each other without going through the base station, without going through the core network. This is very energy efficient. Other benefits for that could be, for example, resilient communications. So Marty mentioned that earlier. In the event of a disaster, communications, direct communication between user terminals would be very important, a way of keep the communications operation going. Of course, everyone talking about AI. Again, for the first time, 6G will be AI nascent. So from a nascent design of the architecture to the lower level reconfigurable antennas, everything will be driven by the intelligence. So of course, there are many reasons people talk about, but to me, these are the main reasons why we should have 6G. By the way, I had the pleasure to collaborate with Professor Marty on the invited paper for 6G antennas. So if you are interested, you might take a look. Here we talk about why 6G is important, why certain antenna technology will be required for 6G. So I mentioned the ubiquitous sensing earlier. Actually, we have been working on this for 8 years now. Probably because in Australia, we have constant problem with natural disasters. Actually, flooding and fire are two most detrimental natural disasters to our economy and to our communities. So recently, based on our research, we established a TBG Telecom and UTS Network Sensing Lab to transform, to start with, TPG's mobile network into ubiquitous flood and storm sensors. So I mentioned the problem with the sensors earlier. So there are a lot of issues with the current way of monitoring the environment using physical sensors. The first one is installation, power supply, and maintenance of sensors. To give you an example, to manage flooding, we need to have sensors for monitoring flooding, naturally. But the installation of flood sensors everywhere in the world, in the wilderness, is pretty much a big challenge. So because to start with, you need a power supply, then the maintenance afterwards would be a tremendous task. One also important issue with this is the scalability of sensor networks. So again, in order to monitor the whole New South Wales, part of Australia, one of the biggest states, if not the biggest state, we need billions of sensors to be managed and powered. Also need to be networks, so we can collect data. That's a task probably not accomplished by traditional method. Therefore, the traditional method is not scalable. The resilience of sensors is actually also an important issue. In the very event, if there is flooding, for example, the sensor will get easily destroyed, washed away. Then they're not working anymore. So that's not the issue. Also, the last, not least, is the connectivity. All sensors need to be connected so we can get the data, analyze the data, and predict the future events. So because of all these issues, the current sensing technology do not have temporal resolution or spatial resolution we require for flood sensing. To give you an example, if you ask the let's say, weather forecasting system, what will happen in Sydney in, let's say, in the next 7 hours, we can easily get that data. Say, by average, how much rain we might get, that we can get that data. But you pin down for any specific street and any given time, say, how much rain is going to fall in that street? What's the risk of people getting flooded in that small area? Then there's no way of telling this right now. So this leads to the AI-powered ASAC for climate adaptation. Using the mobile networks, we can do all the sensing we need without the need for dedicated sensing infrastructure. This one is definitely very well suited for wide area sensing. We can have 24/7 operations and all weather operations without worrying the sensor might be washed away or destroyed. It can be used not only to monitor water, let's say rainfalls and water level on the ground, but also can be used to monitor the soil, crops, water, resources, vegetation, etc., etc. Therefore, 6G is embracing transport sensing as one of the hallmark features. So 2 years ago, funded by the New South Wales government, we started a major project called Flood and Storm Intelligence. The idea is that we will use TPG's mobile network as a weather sensor, and in combination with other data, for example, the Bureau of Meteorology and the historical data, which the government has, etc., to build an AI-powered digital twin model. That digital model can, firstly, enable us to observe what's happening in real time, in a localized manner, but also predict what will happen in the near future, in the next minute, next half an hour, next day, etc. So this one has been a great success. We have been achieving some groundbreaking results. An example is shown on this slide. On the right, you see the yellow graph. The top red line is basically a model we generated. The yellow underneath is the ground truth. You can see once they trained, we can predict the rainfall very accurately. That's one example. Of course, we can also use AI to get other statistics. So one particular example, you can classify the rain as heavy rain, light rain, etc. Also, one thing to note is that not only we can use mobile networks, but we can also use Wi-Fi. As long as you have wireless signals bouncing around, you can get this information. So this is pretty cool stuff. Before I move on, perhaps for people who are not familiar with this area, you might ask, why is that possible? The reason being, if there is a wireless signal bouncing around, at the receiver, whether that's the base station or your mobile terminal, your signal will change according to how much rain is falling, how much water is on the ground, what has changed by, for example, landslide, the moisture in the plant, etc., the movement of the trees. So all this information is embedded in the radio signal. If we can harvest information from the radio signal, we get almost everything we want. That's the fundamental sense of network sensing for flood monitoring. So now we move to some 6G features which are directly related with antennas. The first one is called ubiquitous coverage. So I mentioned earlier, the 6G will embrace the convergence of LEO satellites and even other satellites and other platforms such as high altitude platforms, HAP, as one known, and drones, etc. Combine this with the terrestrial networks, so we'll have ubiquitous coverage. As a result, the antenna designs need to accommodate those needs, and different platforms would have a different requirement on the antennas. Therefore, there's great opportunity and challenges for the antenna researchers to deliver that ubiquitous coverage feature of 6G. The second one is network sensing or integrated communication sensing. So I mentioned by harvesting information from radio signals, we can get sensing data. But how to get the data, it depends on the antenna beam pattern. We talk about, for antenna researchers, the beam pattern is something we talk about the first. So you can have a different kind of beam. For example, you can have a wide beam, will collect all the information from the surroundings. But this information will be very, very rich. But because it's too much information, perhaps the accuracy may not be as high as you need. So for example, if you want to get information from a particular angle, then you want one beam. If you want to have, let's say, track multiple vehicles for different applications, then you might want to have a multi-beam tracking different moving objects. So how to design this antenna which have adaptive multi-beams and also combination of narrow beam, wide beam, etc., will be a challenge for antenna designers. We talked about AI nascent 6G design. Reconfigurable antenna has been a major antenna research field for over 2 decades. But up to now, it's mainly remained in research labs. Again, perhaps the first time in the mobile network, wireless network, we'll be able to use reconfigurable antennas as actual internet solution. The reason being, with the AI as you see, the brain of the 6G, then we'll be able to reconfigure everything from the network architecture to the antenna itself to suit for the radio propagation environment. For the enhanced Starlink communications, which means device-to-device communication directly, definitely we need to have low cost, low energy consumption to create multi-beam antennas or a multi-beam pattern created by those antennas, which can connect with each other, communicate with each other with high performance. So this gives us new challenges. Low cost, low energy basically means the traditionally powerful digital technology may not be applicable. We need to create new techniques. The last one is the terabits per second data rate, which is trying to be achieved by all the researchers right now, including group here. So to do that, we need several methods. One is that we need to use higher frequency spectrum. So currently, the identified spectrum for 6G is kind of new one, is centimeter frequency bands. So this can't need new antenna designs. More importantly, as you might have noticed when you go around, all the mobile base stations have many antennas. So currently, all the antennas are supporting 4G and 5G. Some of them are still supporting 3G. All these different systems have different antennas. Putting them together in a tight space actually is a very challenging task. So antenna co-location has been a challenging task for the antenna designers since the beginning of the 3G. So what are the problems? So physically, if we don't think about the performance, you say, okay, I can put them as close as possible. But actually, when you do so, there are 2 problems arising. The first problem is strong coupling. That means the antenna signal from one system will go to another system. So you have strong interference from each other. A second problem, which was unknown until recently, was called beam pattern distortion. This was well known in industry, but not well addressed by the academic researchers. The issue is that in order to have proper coverage, ideally, we have, for example, sectorized antenna patterns. So when you change from sector to sector, the coverage is maintained well. But if you put antenna too close, then the beam pattern will not be as clean as your ideal sectorized beam patterns. So the closer they are, the more severe the problem becomes. So the solution is called descattering. So we have been working on this for a number of years. We may regard ourselves as the pioneer in descattering techniques. So going to 6G, to start with, the base station will support 4G, 5G, and 6G. Gradually, you drop 4G, then start supporting, let's say, 5G, 6G, and 6G advanced. So as you move on, as the evolution happens, you always need to support multi-band, multi-generation antenna systems. So this multi-band antenna collocation is a challenging task for the antenna researchers. A couple of years ago, we were brave enough to publish a book called Advanced Antenna Array Engineering for 6G. Back then, the 6G landscape was not clear as today, but some of the topics we touch are still quite relevant. For example, the antenna collocation, multibeam, etc. So at UTS, as mentioned, we have one of the biggest antenna research groups, arguably in the world. We work on many antenna systems. For example, reconfigurable antenna arrays. We've been working on this for almost 2 decades. We've been working on digital multibeam antenna, not digital, sorry, analog multibeam antenna arrays. Again, this is probably one of our major leading areas. We're working on conformal transmit arrays, tightly coupled ultra-wideband antenna arrays, metasurface-based antennas, base station antennas, etc. You might notice the right bottom actually is a commercial antenna for current base stations. The big antennas are for lower frequencies. The small antennas are for higher frequencies. They are all put together into one case. So we actually provide some decoupling technique to that particular design. This antenna, to my knowledge, has been used by Nokia and Ericsson naturally in Finland, I would assume. Okay. So the next focus of my talk is now on analog multibeam antennas. So why analog? We are in a digital era, yes? Yes, we are. Digital is powerful, but to me, analog is more beautiful and energy efficient. That's my motto. So with the digital age, with it's a broadband, high speed, wide communications, we all need ADCs, right? DACs, all these heavy signal processing, they are powerful, but they consume a lot of power. If we can do some of the tasks required currently by the digital technologies, instead doing them in analog manner, we can save a lot of energy. So for this reason, we've been promoting analog beamforming, particularly multibeam antenna technologies for 6G for a number of years. So these 2 review papers we published since 2021 have been well cited and read, seem to be making some impact. Before I dive into the pure digital, perhaps we should talk about the hybrid array first. So what is a hybrid array? There are many definitions, but in the context of my talk, a hybrid array is a combination of analog subarrays and the digital beamform techniques. In other words, each subarray is an analog array. Then all the output for the receiver will be combined digitally. These 2 kind of techniques, digital technique and analog technique, work hand in hand to create a hybrid array architecture. We have been promoting this since in 2010 when we published the first paper about this architecture. To my understanding, this architecture is being used by 5G millimeter wave of all the major vendors right now. So that means even we talk about analog, we are not saying the digital technology is not useful. We're saying combine these 2 technologies together in a clever manner might give us the advantage of saving energy and saving cost. Because there are many analog techniques for antenna designers. But here I'll focus on the multibeam antenna techniques. So there are 2 types of multibeam antenna techniques. The first one is called quasi-optical multibeam antennas. Basically, they are for high-gain, higher frequency antennas. The second one is called circuit-type multiple beam forming networks, or analog multibeam antennas. This is based on RF circuit. So this one is for lower gain, smaller area for the small form factor antennas. So going to the future, perhaps we will see more reconfigurable, more adaptive, and compact structures, perhaps combining these two technologies together to meet the requirement of 6G systems. For the quasi-optical multibeam antennas, here are the list of possible antennas you might encounter. The first one is called Rothman lens antenna. The second one is called the Roos lens antenna. Third one, Lüneburg lens antenna. By the way, Lüneburg lens antenna is shown here at the right bottom. These have been around for several decades, but only recently industry has shown an interest because it's so easy to create multibeams with Lüneburg lens. And also, Lüneburg lens used to be regarded as too heavy to be of practical use, but the development of material science and technology, multi-metal material, etc., has made that possible. Now we can have lightweight, low-cost Lüneburg lens antenna for creating multibeams. Then we have the multi-feed reflector array and transmitter arrays. The last is the gradient refraction index, green lens antenna, which I'll touch on later. I heard a talk from Marty Group about Fresnel zone antennas. Actually, we were one of the pioneers in that area. So this, what you can see is an offset Fresnel reflector array, if you like. The recoverability can be realized by putting the different blocks or different units together at different places. So what are these blocks? Any guess? They're Lego blocks. So back then, this concept was known in books, but not well known by the public. So when we tried to build the first reconfigurable Fresnel zone-based reflector array, we came up with the idea of using Lego blocks as the base, then put the different metal layers in with dielectric in between to realize the phase shifting values. This one was arguably the first reconfigurable reflector array, if you like. So because we use Lego at the time, the BBC was quite interested. So they put us in a BBC program for the public. Quite interesting. So there are reflector arrays and transmitter arrays. Some of the technology are for both. Some are unique for one of them, one of the two. Broadly speaking, transmitter arrays have the advantage that you put the feed behind the plate or the surface. Then you do have the blockage issue between your feed and the radiation field, because the surface in front of the feed and the radiation goes in front of the surface. So it has that advantage. For many platforms, that is desirable. From the technical point of view, transmitter arrays are more challenging. The reason being, for reflector arrays, you can always have a perfect reflector placed behind all the phase shifting elements. As a result, the efficiency is always high. But for transmitter arrays, it's very, very hard to avoid reflection back from the surface itself. So you have to make sure most of the energy is going through and then radiated rather than reflect back, then wasted. So for that reason, there are more papers recently on transmitter arrays. So one of the work we conducted was to build a wideband, so tightly coupled Huygens elements. So what's a Huygens element? So if you have a surface in front of your feed, because the the permittivity of the dielectric is different from that of the air. So reflection is inevitable. But if we create Huygens element, which consists of an electric dipole and the magnetic dipole as a pair, then you can basically, theoretically, only have forward radiation, not backward reflection. So using two offset electric or conducting strip on two sides of dielectric, you can create a Huygens element. By putting many of these elements together, you can realize a high-efficiency transmitter array. For this particular piece of work, we put a number of different lengths of Huygens element together. To get them tightly coupled, we realize not only high transmission efficiency, but also high bandwidth. So this is one of the work we published. If you want to go further to have a wider bandwidth, you can have even more complex structure. For this one, we have ultra-wideband employing connected slot bow tie elements. So these meander lines, basically in the middle, give you the phase shift value you need. The tightly coupled bow tie element give you the wide bandwidth. Altogether, you can reach from 6 GHz to 17 GHz for this antenna. So for transmitter array, this is quite hard task. So here shows the prototype we built. Another interesting topic for 6G would be electronically controlled beam scanning, metasurface antennas. So there have been lots of efforts to do this. The fundamental idea is that we reconfigure each element. Therefore, their phase shifting value would change from place to place. Then we can create a phase pattern, if you like, as this, similar to Fresnel zone, because the principle is the same, as you see. So you can, depending the change of this pattern, you can have the beam pointed in different directions. So based on this principle, we use the offset electrical strips, which I mentioned earlier, to build beam steering, beam scanning metasurface antenna. So this one, basically, because we use switches, the pin dials, so it's a 1-bit kind of phase composition technique, meaning you either have 10 or 180 degrees. So as a result, the design is very simple. So, but regardless, as you can see at the bottom right, beam scanning was realized. Another interesting technology for lens antennas is called a gradient refraction index, meaning that you can, as shown on the top of the right figure, you can have different dielectric in different rings. You put all this together, you have a green lens. The advantage of green lens antenna in comparison with others, such as Lüneburg lens, is that it's flat. So being flat, it can be easily integrated into many systems. So on the right, you see a multi-beam green lens antenna we published in 2023. This is probably one of the earliest multi-beam green lens antennas. But you can see there are still issues, although the idea was quite interesting. So the basically the feet are placed on some arcs. For different beam, you use a different element, a different location of the arc. So all the lens is compact, but the feet is not compact. So as an academic exercise, it was a great achievement, but for practical applications, may not be ideal. So currently, we are developing technology to make the feet flat as well. So as illustrated here on the right side. We are making very good progress. So we are confident we will be able to achieve that. So earlier when we talked about lens antenna with Professor Marty group, we talked about beam scanning, multibeam, etc. So we believe this might be a good way going forward. So you have basically the electrical circuits below the feed layer, then the feed layer itself is flat. The green lens itself is flat. So you have a flat, compact architecture for such antenna. Now I move to the second type of multibeam analog antenna. It's called circuit type. By circuit, I mean the RF circuit analog. So traditionally, there are three types of circuit type multibeam antennas. Right. The first one is called Butler. Everyone knows Butler matrix. Even people in digital communication are familiar with this. So idea is that with Butler matrix, you can create m number of orthogonal beams. Being orthogonal means that every peak of one beam would be at same location as 0 other beam. That's the definition of orthogonal for the Butler matrix. As such, with such a feature, Butler matrix have been widely used in 4G and 3G. But the problem with Butler matrix is that all these beams are fixed. The beam crossovers are fixed. So that's the disadvantage. The advantage of Butler matrix is that it's lossless. In theory, it has a wide bandwidth because it's a parallel architecture. The second type of circuit type multibeam antenna feed system is called Blood's matrix. It's a rectangular matrix, as shown on the top right. It has loads, match loads or resistors in the implementation at the right and the bottom, you can see. So as a result, it's regarding being lossy and has not been widely understood or investigated for a long, long time until recently. Actually, recently we proved in one of our publications that if you design the Blood's matrix in a clever way, then the lossy can be managed to a small value. The efficiency can be well over 90%, for example. The third well-known circuit-based multibeam antenna architecture is called Nolan matrix. In comparison to Blood's matrix on the right, the Nolan matrix at the bottom has a triangular structure. That means everything at the bottom triangle of the Blood's matrix has been removed. All the resistors or the mesh loads have been removed. So it's lossless in theory. This, in contrast to the Butler matrix, it can create beams in any desired directions. So, because now it's lossless, it can produce beam in any directions. This makes it quite desirable to communication and radar applications. So, if you read you check the public literature, you see that most recent research activities are focusing on this Nolan matrix. Even some communications people are starting to pick this up to investigate the performance you might be able to achieve with Nolan matrix. So these are great progresses. However, there is one problem with all these historical or classic architectures. They are all designed for fixed beams. But going into 6G, as I mentioned earlier, we need to have dynamic beam to follow different objects, different users. Then this kind of structure wouldn't be able to provide that functionality. In theory, you say, okay, maybe I can reconfigure everything, then I can have my beam steered. But if you do so, to give you a sample in the instance of Nolan matrix, you would reconfigure every phase shifter involved. So your control circuits will be over complex. That's unrealistic. In order to solve the problem, we need to address certain challenges. Before I get into the details, just because there are a lot of student research here, here are a list of major problems with current matrix circuit type multibeam antennas. The first one I just mentioned, independently steering every single beam in a multiple beam structure is impossible with 3 classic architecture. Then there is the bandwidth limitation, especially for the Nolan matrix and blast matrix, because they are serial-fed architecture. The third challenge is 3D beamforming with 2D arrays. So most of the published work on those 3 matrices are for linear arrays, with a few exceptions. But in practice, you need to have a 2D array to do 3D beamforming. So there are some progress most recently, but generally speaking, these are still unsolved problems. There are another fundamental problem for all the circuit-based architecture is that the low-loss circuits, especially low-loss phase shifters, has been challenging for everyone, from industry to academia. So these are the challenges we have to resolve to make circuit-type multibeam antennas practically useful. In the next, we'll address the first problem, the independently steerable multibeams make that possible. So we came up with a new architecture called the Generalized Joint Coupler, or JGC matrix. So this one, the JGC matrix, can fit an antenna array. With this, you can have independently steerable multibeams. So the reason that can be achieved was because the architecture put the phase shifter in such a manner that each row of the matrix will have the same phase shifters controlled by same voltage. Then to change one beam, you just change the voltage of the associated with that particular voltage. Through theoretical analysis, we proved that in the first order approximation, all these multibeam are independent, meaning you can simply change one beam without affecting other beam. That makes it desirable for practical applications. So for all the publications listed here, we provided some systematic theory for synthesizing such a matrix, or also the theory for designing both transmitting and receiving JGC matrix and other theoretical concerns people might have. So this is still working in progress. We are still working in area, for example, making the JGC matrix more broadband, also low-cost, compact 2D structure. So just a quick look, what are the JGC matrix? Effectively, there are 2 types of JGC matrices. One is called blast-like. If you look at the left, it's a bit like blast matrix, but it's different. The main difference you see is the position of phase shifters. If you look every single row, it's like a phase array for one single beam. You combine all these together, you have phase multibeam antenna arrays. So we are all familiar with phase arrays, which have been used in communication radar, but we probably are not familiar with phase multiple arrays. So this is the way to realize that. On the right is a Nolan-like JGC matrix. Again, it looks like Nolan matrix, but again, the phase shifter are placed in different locations. Also, now we have the flexibility, make it make it flexible that we have arbitrary number of inputs, arbitrary number of outputs, whereas for the Nolan matrix, the triangular matrix, the input, the number of beams is same as the number of the outgoing output. Here, you see the antenna number elements can be designed arbitrarily and not necessarily constrained by number of beams. So this is the another advantage of the Nolan-like GGC matrix. So as I shown you, we have been doing research for a number of years since we published first paper. The findings to date are as follows. First one, the performance of the beam depends on the N, which is number of antenna element, M is number of beams, demand ratio. The bigger the ratio, the more flexible we have, the more flexibility we have. The same way, the GGC matrix can realize very low side lobe beams. A typical the classical structure typically give you around 12, 10 dB, but this one, you can theoretically realize any low side lobe levels. Also, the GGC matrix can produce beam with deep nulls. So this can be used to minimize inter-beam, inter-user interference. The next feature is that all these beams can be steered individually, independently. Another feature is that we can use the Nolan-like GGC matrix to produce orthogonal beams. This offers a new capability beyond the traditional button matrix because the complexity of this is lower. The last one is, although the GGC matrix, a bit like a blast matrix, involve the utilization of certain match loads or resistors, but theoretically, we can prove that you can achieve very high efficiency in both the transmitting and the receiving mode, and we can demonstrate that through experiments already. Another interesting movement for that GGC matrix design is that we can now, the rectangle on this diagram are couplers, directional couplers. Traditional couplers, for traditional coupler, you only have one parameter, theta. Then the phi is to do with phase shifters, typically independent of the coupler design. We found out that by introducing another parameter, phi, into this coupler design, then we can achieve better performance. So that's kind of what we call the modified GGC matrix. Here it shows some very low side lobe designs using blast-like GGC matrix. You can see the side lobe levels are below -25 dB. So you can use different kind of transmission line technology to design the GGC matrix. In that instance, we use strip line technology to do it. For this design, we use a microstrip to do it. That was the first realization, actually. Now we are working on higher frequency, for example, millimeter wave design of this GGC matrix. Also, this is one of our experiments. As you can see, as we would expect, the experimental results are very similar to the predictions. So here are some conclusions of my talk. Owing to their low cost and low energy consumption, analog multibeam antenna may serve as a major candidate for beyond 5G and 6G. Most current analog multibeam antennas are for fixed or switch beams. So creating individually controllable and simultaneously steerable multibeams is a great challenge. The GGC matrix offer one solution. Okay, yeah, it's always tricky to draw conclusions. Yeah. So the GGC matrix and its related hybrid architecture may provide a way forward for many demanding requirements from 6G. 6G is providing a golden opportunity for innovation in wireless communication and sensing antenna propagation in particular. So because it's so challenging, it's causing quite a few glitches here. I don't know why. Integrated sensing communication ASAC is of particular importance to both research and environmental sustainability. So for me, I'm very passionate in embracing ASAC, in making ASAC technology beneficial to our society and to our humanity. Thank you very much.
Thank you again, Professor Guo. And yes, for a nice presentation. And maybe we have time for one question, maybe. Yeah.
Thank you for your great presentation. As we discussed briefly earlier, you had some years ago this NGARA project in Australia targeting at remote connectivity solutions. And beamforming played an important role in that concept. So since most of the people here, they are not aware of that project that happened years ago, can you give a brief summary of the main aspects of this NGARA idea and targets?
Okay, sure. Yeah. Communications in the wide area of Australia, in rural, regional areas, has been challenging. I have been told that coverage in Finland is not a problem at all, but I learned from Marty, it's not perfect yet. But in Australia, many parts of the world, Australia do not have coverage. Right? But many people, especially rural, regional communities, they live in area where you do not have adequate coverage. So we have the problem called digital divide. So a few years ago, when I was at the CSRO, that's our national research agency, we started a program called NGARA. That's a kind of indigenous word mean to listen, to hear. So we address two main problems. The first problem is, in order to connect remote communities, you need to have a wireless fiber, so to speak. Meaning you can't lay fiber because laying fiber for thousands of miles across different terrains is just impossible. So we have to have a wireless fiber. So we developed technology which to deliver, back then, gigabits per second data rate across a wireless signal channel using E-band. Right? So that's one technology. That one actually has been used, but to our surprise, for a different purpose in the US, for stock market trading. They use that high bandwidth, low latency. So that's kind of a different application, but we designed the technology to serve our remote communities. That's one technology. The other technology is access, meaning we have this wireless fiber connecting from cities to rural areas. Then at any village of interest or community of interest, you have this access point. Then at this access point, you have multi-user MIMO. So to beam all the signal to different households so they can have a wireless internet. So all the wireless from end to end, from the user all the way to the cities or the communication hubs. So back then, again, one of the most powerful multi-user MIMO we built back then. So that was quite cool. So we commercialized it to a company, but unfortunately, none of those two technologies have been used for the intended purpose. But now, Professor Martin knows, we established something called New South Wales Connectivity Innovation Network. The mission is, one of the missions is to deliver broadband and connectivity to rural regional areas. So we are thinking of some piece of technology, although it's now more than 10 years old. Some of the components are still quite advanced. We might pick them up, then develop new solutions, more desirably together with your team here. Okay, thank you.
Okay, I think I'm sure there's more questions, but due to the interest of time, we will need to conclude for today. And please feel free to write or approach Professor Guo via email. And yes, I thank you once again for your attendance, and thank you again, Professor Guo.
Thank you very much.